April 6, 1945, dawned over the East China Sea, with Task Force 58 of the United States Fifth Fleet spread like a constellation of steel and smoke. Far ahead of the carriers and battleships, radar picket destroyers sat 16 miles out, lonely sentinels scanning the morning haze for the shape of things to come. On the USS Lee, men in the Combat Information Center watched their scopes and felt the air thicken with dread. Contacts, not dozens, but hundreds blotting the returns. The gunsmen below deck readied 5-inch shells stamped with the enigmatic letters VT, miniature thinkers inside each shell that would, in a few frantic hours, reshuffle the odds of survival for the fleet. The mission that morning was Operation Kikusui 1, the opening chord of 10 massive, coordinated kamikaze assaults that would hammer the American Armada off Okinawa. What followed was not simply a clash of planes and guns, but a demonstration of how a single electronic innovation had come to define modern anti-aircraft warfare. The Japanese assault was an act of both ingenuity and desperation. Having lost carriers and veteran airmen in successive defeats across the Marianas and the Philippine Sea, Japan turned to special attack units as a force multiplier. Pilots with little training, but with a singular, terminal objective. Early kamikaze strikes had produced terrifying results. Hit rates that conventional doctrine put at about 2% ballooned into much higher percentages when attackers were deliberately crashing into ships. A single zero with a 250-kilogram bomb could, in theory, cripple a destroyer. A single pilot could trade one life and one obsolete airframe for the loss of hundreds of sailors and millions of dollars in damage. The expectation that a suicidal pilot could restore parity arose from brutal arithmetic and grim strategic necessity.
Yet the Americans had a different kind of arithmetic in their favor: electronics plus industry. The VT proximity fuse, a tiny radio transmitter receiver and sensing circuit burrowed into a shell, removed the need to estimate exact range and set mechanical timers. Instead of guessing when a bursting shell might shred a plane, gunners could fire and let the shell decide when it was close enough to detonate. The concept had been honed in a crash research program begun in 1940 at Johns Hopkins Applied Physics Laboratory, and after 3 years of hard lessons and battlefield testing, the device had arrived in the Pacific fully matured. The technical problem had been monstrous: tiny vacuum tubes, batteries that would activate under massive acceleration, and circuits that could survive 20,000 G and spin rates hitting tens of thousands of revolutions per minute. The tube's glass, the solder joints, the electrolytes, everything had to be engineered to impossible tolerances. Yet by April 1945, American industry had produced millions of these fuses, distributed across dozens of firms and factories, the product of a national effort on the scale of the other great secrets of the age. Manufacturing scale amplified the technology's battlefield effect. By the Okinawa campaign, millions of VT fuses had been turned out and distributed to the fleet. Allocation rose from roughly a quarter of anti-aircraft ammunition in 1943 to 3/4 by 1945. Crossley, RCA, Eastman Kodak, General Electric, and many others were mobilized. Production lines were retooled, workers labored around the clock, and cost per unit plummeted with mass production. What had once been exotic and expensive electronics became routine, reliable, and ubiquitous aboard every destroyer, cruiser, and battleship. The fleet's defensive philosophy evolved accordingly. Shield the ships in concentric rings, push early warning outward with radar pickets, and let overlapping VT-armed 5-inch batteries create zones through which attackers simply could not pass.
When the first Kikusui wave reached the pickets at 0600, the theory became cruelly clear in practice.
nearly 400 Japanese Navy aircraft and more than 100 Army planes participated in the operation, and of those, nearly 300 were designated for suicide. Pickets picked up swarms on radar and opened fire at maximum effective range. The proximity fuse turned near misses into kills. A shell that passed within lethal distance no longer needed a perfect time setting. It detonated on its own and filled the sky with lethal fragments. That morning, reports cascaded in of aircraft shredded in mid-approach, of pilots whose missions ended miles from their intended victims. Destroyers fired continuous belts of VT rounds, switching targets rapidly and creating what crews came to call walls of explosions. The experience of ships like USS Laffey and others became case studies in the fuse's power. In prolonged attacks, a destroyer could pour hundreds of VT rounds into the air in minutes, each round an autonomous interceptor creating lethal puffs at the predicted point of nearest approach. Even kamikaze tactics, intended to beat early warning, low, wave-top approaches meant to mask radar returns, were blunted when shells detonated at low altitude and sprayed fragments across the sea. Ships that were struck and survived often credited proximity-fused ammunition with reducing damage or buying the time needed for extraordinary damage control. The paradox was stark. Suicide tactics, devised to negate American numerical and technological advantages, were suddenly confronting a weapon that delegitimized their most basic assumptions.
Historical firsts underscore the fuse's operational pedigree. The concept had proven itself in combat testing as early as January 5, 1943, when USS Helena fired the first proximity-fused shells in action off Guadalcanal and downed an attacker without a direct hit. This validation rippled back into laboratories and factories. The electronics were refined. Manufacturing defects were chased down. Batteries, tubes, and antennas were made rugged. By Okinawa, a single VT burst could have a lethal radius far greater than a time-fused shell, and the number of rounds required to knock an aircraft out of the sky plummeted. Where time-fused 5-inch shells might demand over 1,000 rounds per kill in the worst conditions, VT fuses reduced that average dramatically, sometimes to mere dozens, occasionally to just a handful in well-placed bursts. The psychological effect on kamikaze pilots was almost as decisive as the physical. Survivors and aborting pilots described approaching ostensibly intact task forces only to meet clouds of exploding shells that seemed to spring into being at impossible points in the sky. Those black puffs, appearing with uncanny accuracy, demolished the illusion that a pilot could find safe corridors by varying altitude or angle. Japanese doctrine adjusted. Pilots were ordered to approach from above and plunge vertically, to mass attacks from multiple axes, to seek the cover of night. But each adaptation created new vulnerabilities. High-altitude dives exposed attackers to longer radar tracking and fighter interception. Dawn and night approaches reduced accuracy. Every tactical tweak yielded diminishing returns against an integrated system of radar,